So good morning. I am Krishna Kumar from Krishna's classroom. We continue with the investigations on the structure of the space of all linear transformations from Rn to Rn. We have already seen that this is a vector space. So we already know that L, Rn, Rm is a vector space of dimension n. Now we want to explore this space further, and we have proved that A belonging to L, Rn, Rm implies log of A is less than infinity. That means we call this all linear transformations from all linear transformations like this are bounded. In fact, they are uniformly continuous. A is uniformly continuous. This is what we proved last time. In fact, the remark is that this results not in general true for linear transformations on infinite dimension spaces. Now this is just a caution, because when you deal with infinite dimensional spaces, you need not expect this result to be true. That you get more, challenging scenarios, and you will have to deal with the infinite. You will have to deal with unbounded operators. A typical unbounded operator is a differential operator, like Schrodinger operator. I think I'll stop there with that comment, and then now we pursue the following. So we want to prove the next result, that is actually looking at the structure of L, Rn, Rm. We prove that L, Rn, Rm is a non linear space, and consequently a metric space. Now, this is the important point. If you look at this space, you have already seen that it's a linear space. In fact, now we want to show that it's a non-linear space and therefore a metric space. The consequence is that simultaneously there are two structures on this collection of objects. What are they? One is an algebraic structure. The other one is a topological structure. Therefore, see, you can comfortably do analysis on these objects. Okay? So that's the important thing. So we prove this result. Now for that, what are things you have to prove? The first thing that you have to observe is that norm of A. What is norm of A? Okay. Norm of A is defined as supremum of this is the norm on Rn, this is the norm on Rn. Okay, now we want to prove that this defines this is the definition. Now this defines a norm. Now for that we have to check a few properties. So to check that, one of the properties is that norm A is greater than or equal. The second property is that norm of A equal to 0 if and only if A equal to 0. Okay, the first one is obvious from the definition. The second one tells if norm of A equal to 0, then norm of Ax equal to 0. And this is true for all x with norm x less than 1, and from which you can use this property that A of any y equal to, if y is not equal to 0, then this is equal to norm of y into A of now this is the problem. Okay. Therefore, you know that this is with this is equal to norm of y into A of z, where z is equal to y divided by norm y, and you know that norm of z is equal to 1. Therefore, you see that this is 0. So consequently, Ay equal to 0. So for any y belonging to Rn, Ay equal to 0, which in turn implies A equal to 0. So that's fairly simple. Okay. Let me just go to the next property, which needs some work. Third property is that Now this is simply by writing it you get it. In fact, you see that norm of is equal to norm of ax plus bx two, and this is less than or equal to norm of bx. And therefore you see that this is less than or equal to norm of ax is a norm of a into norm of x plus norm of b into norm of. Now this is less than or equal to norm of a plus norm of b now this is true for every x. Okay, this is true for every x in R. Okay, so you take the supremum. Okay, therefore this is true for supremum of this over norm x less than or equal to 1. You take supremum. Therefore you get because we are taking norm x less than or equal to 1, so you get this less than or equal to 1, so you take the maximum value and therefore this bound is there. This implies so one of the crucial properties of a norm is now satisfied. Okay, now we have to show that this is the third one. Now the fourth one, we claim norm of ax, norm of CA equal to mod C times norm of. This is what we want to do. Now to prove this, what we do is the following. So first of all, when C equal to 0, this is trivial. When C not equal to 0, you consider this. Now what do you get? You get norm of CA is less than or equal to mod C into norm of A. That's quite easy to prove. Okay. Now we want to get the reverse inequality. To get the reverse inequality, for the norm of A is equal to norm of 1 by C into CA. But we are assuming C is not equal to 0. Therefore, this is less than or equal to 1 by mod C into norm of CA. Okay? So, which implies norm of CA is also greater than or equal to mod C into norm of. Therefore, together, hence, together, we get for every C belonging to this. Okay, what more do we want? So for all A belonging to L, Rn, Rm, and for all C belonging to this is true. Now we want to show that this is a metric space. So to show that this is a metric space, all that you need is define row of you know that A is a linear transformation, B is a linear transformation, A minus B is well defined, so it's also a bounded linear transformation. It is in the same class, therefore its norm is defined, and we take this as row AB. Then row is A on okay. So what are the things you have to show? You have to show that row AB is greater than or equal to 0, obvious. Row equal to 0 if and only A equal to B. This is true because row AB is norm of A minus B. Norm of A minus B is 0, implies A minus B is 0, which implies A equal to B. Now row of AB equal to row of BA, that is also really true because norm of A minus B is the same as norm of B minus A. Now the fourth property is triangular inequality. Now you see that norm of A minus B is equal to norm of A minus C plus C minus B. Now this is less than or equal to norm of A minus C plus norm of C minus B. As we have proved here that norm of A plus B is less than or equal to norm A plus norm B. So we are using that. And therefore, row B for every A, B, C belonging to Therefore, rho is a metric. That is, rho is a metric, and therefore L, Rn, Rm is a in fact, just one line would do. Every normally linear space is a metric space. Therefore, this is a metric space. But I just gave the proof. Now, this is how you give the proof in the case of a normally linear space to show that it's a metric space. This is the proof that we give. Okay, fine. So what we have now? We have now on L, Rn, Rm is a metric space. It's a linear space. It's a linear space of dimension Mn or Nm, whichever way you want to write it. Okay? Well, so there are two structures on it. One is a linear space structure, the other one is the metric structure, which is a topological structure. And therefore now you can talk about all kinds of things like open sets and so on. And then of course you have the advantage to talk about functions defined on that. You can discuss concepts of continuity, etc. So you see that there are two things that you can immediately prove, that the vector space operations are continuous. For instance, you see addition and multiplication and scalar multiplication are continuous operations from x cross or Rn cross Rn to L Rn cross. Okay, let me write this here. So if I write x then you see that addition is a map from x cross x to x. We can show that that addition is a continuous map from see what you have is that on x is a metric space. So from x cross x, on x cross x you can introduce a metric, and therefore this is a metric space. This is also a metric space. So you are talking about maps from x cross x into x, and addition is one such map. And what you can prove that this is continuous. In fact, all that you prove is this: if An converges to A, Bn converges to B, then An, Bn An plus Bn converges to B plus. This is the thing that you want. Okay, that means rho of goes to 0, rho of as n tends to infinity implies rho of zero infinity. Similarly, one can show that C A scalar multiplication continuous operation that is CM that you write in terms of the row and then so I leave that completely discussion. These are some of the points. The next remark is this. The next theorem, A belonging to and B belongs to L, Rm, Rk. Ba is defined. So this is the next slide that we want to do. So we look at the proof of this. Calculate this. Ba of x is equal to B of which is less than or equal to norm B for every belonging to and from which it immediately follows that norm of BA is less than or equal to norm of PA. Okay. I want to caution you a few things that here the norm is in RT. Because where do you reach finally? See, you are going from Rn to Rm, Rm to Rk. So this is what you have. You have Rm, Rn, start with an x here, A, So you reach here AX. So BA this is the map that you have. So you are talking about, see, there are a few spaces here. One, A belongs to, A is in L, Rn, Rm, B is in L, Rm, Rk, then BA is defined from Rn to Rk. So BA belongs to L, Rn, Rk. Okay, so that is well defined. But AB is not in general defined. AB is not defined, but BA is defined. So for that BA you can mark this inequality. Therefore, the norm that I write here is the norm in Rk. The norm that you have here is the norm in where? In Rm. So the norm that you have here is the norm in Rm. Here the norm is in. Okay, so that's something to be observed. So this is true for every x belonging to Rn. Therefore, you see that it is true for suprema with the norm x less than or equal to 1, and therefore you see that norm of BA is okay. So that completes the proof of that. But what is significant about this? Suppose you take n equal to, look at this case. Then you have L, Rn. So that's the map that you are working on. So on L, Rn, you see that if A, B belongs to L, Rn, then both AB and BA are different, and are in Rn. So you have got both this inequality defined for both AB and BA, but AB may not be equal to, in general, not equal to you would have seen this with the matrices. The matrices do not commute. Therefore, A and B do not commute in general. So what do you have now? You have a linear space structure on L, Rn. You have a multiplicative structure on L, Rn. What is that? Both AB and BA are defined. Given two linear transformations, you can talk about the product of that, which again gives you another linear transformation on the same space. Okay? So there is a multiplicative structure and it satisfies this particular inequality. And that's what we have proved. So you have now two things. There is the addition, scalar multiplication, and multiplication of the operators. Not only scalar multiplication, multiplication of the operators. Okay, so you have three operations already there. One is addition, the other one is scalar multiplication, the other one is a product of linear transformation. So this is what is called a algebra. So you have a multiplicative structure for addition, scalar multiplication, and multiplication. And it is non-commutative with respect to multiplication. Therefore, LRN is a non-commutative algebra. This is one of the properties that we have. Okay, so norm of AB is less than or equal to norm A into norm B. Okay, right. Okay, so that's something about the topological structure. Now, having got the topological structure, next start talking about certain subsets of that. So you consider, so we work on what are called invertible operators. So we look at all A from Rn to Rn, which is 1 to, or equivalently of course A belongs to, you know that you have already seen that if A is 1 to 1, then it is on to. If A is on to, then it is necessarily 1 to 1. Therefore, what you have then A inverse exists as an element of that means it's a linear transformation on Rn, and you have A inverse equal to A inverse A equal to I. So these are called the invertible operators, and not all linear transformations are necessarily having inverses. Because the necessary condition is that if you define a linear transformation, when you say it's a linear transformation, there is no restriction that it should be 1 to 1 or onto. Also, you take projection operators. Okay? Or if the range space is of dimension less than n, then it is not going to be a 1 to 1 onto map. And what is the consequence? The inverse does not exist. So there are plenty of linear transformations which are not invertible. A simple example is the zero linear transformation, which has no inverse. Okay? Therefore, you have a class of linear transformations in LRN which are invertible. Now what we want to look at is what is the nature of the subconnection of invertible linear transformation in this is the question that we are posing next. So let us take, so let is invertible. Okay, so we will designate by omega. So what you have now is the following picture that you have. This is LRN. You have a subcollection here which is omega of all invertible operators. Now we are trying to look at the structure of this. We have already seen that there are plenty of operators in general which are not invertible. Okay. Now we try to look at this collection, some of the nice properties of this. Okay. Before we do that, we go to the simplest of all linear spaces, namely R. So n equal to, consider case equal to. So you are talking about a linear transformation A from R to. What can you say about such linear transformations? Such linear transformation, every such linear transformation is represented by an element of R. So corresponding to A, there is an alpha. It is represented by some alpha. Alpha belongs to R. Okay. So this is very easily established. That is, every alpha belonging to R represents a linear transformation. So Ax equal to alpha. This is the definition. Now, which transformations are invertible? You see that A is invertible if and only if alpha is not equal to 0. So 0 is the only linear transformation which is not invertible. All other linear transformation on LR are invertible. It's a very particularly simple scenario that you have. Okay. Now, so given an alpha, Okay, or given a, let me designate by a not equal to 0. What is the largest neighborhood that you can choose of A in which all the linear transformations are invertible? You clearly see that this is the farthest that you can go. See, on this side there is a restriction because the moment 0 comes in, 0 is not invertible. Okay, so you can move in this direction until you meet 0. On this direction, an equally important thing, but you have no free. You have all the freedom. You can go further than that. Okay, so you can go for, if you take the interval a minus mod a to a plus mod a, okay, then every b belonging to inverted. That is, b is not equal to 0. That's all. Okay, right? This you can say. I mean, on this side, so you can go quite far. If your a happens to be a negative non-zero number, then this is the extent to which you can go, and this is where you can work with it. Okay, so this is the limit to which you can go. A minus mod a and a plus mod a. So this is actually from, if a is positive, this is equal to from 0 to 2a. On the other side, if a is negative, then what happens is that this is from minus 2a to 0. So a positive, then this interval is 0 to 2a. Then a negative, this is from 0 to, from minus 2a to, these are the intervals. Okay. So every b belonging to this is invertible. That's right. Okay. So let us try to explore this further. Okay. Now, so how does this this is the question that you have. How does it generalize to that? Okay, so a is given, which is invertible. Now you can get a neighborhood as large as this until you get to the boundary, so that when you go to the boundary, you get possibly beyond that you start getting non-invertible operators. So what we expect is that given a invertible, there is an open neighborhood of A which consists of invertible operators. And topologically, it shows that for every A belonging to omega, there is an open neighborhood which consists of invertible operators, or an open neighborhood which is completely contained in omega, or in other words, omega is open. Okay? So let us prove that this is possible. So first you have to locate what kind of B you have. So B has to be inside that. Okay? So let us observe that. So what you need is that the distance between B and A. So which way you have a distance between B and A, which is, this is the distance between B and A, has to be less than what? So if B is such that the distance between B and A is less than mod A, then B is invertible. This is an observation that we made in R1. Okay, if B is such that the distance between B and A is less than mod A, then B is invertible. Okay? Or if you start working with A inverse, so what happens? Okay? Right. So if A is invertible, 1 by A is invertible. Okay? Right? Therefore, let me write here that this also I can write as 1 upon A. Absolutely. Okay. Because we have to somehow use the condition that A is invertible. So you have to bring in A inverse. Okay. Right? So A is, we are assuming A is invertible. Therefore, what do you get? Okay. What is B minus A? Mod B minus A is in fact equal to norm of B minus A. Okay? Similarly, 1 upon mod A inverse is equal to 1 upon norm of. Therefore, now let us write this relation in terms of time. So, what do you get? Norm of B minus A into norm of A inverse less than. So, this is the relation. Okay, this relation star is written in terms of norm. Okay. Now let us ask what happens in the general case. In the general case, we take L, Rn. We have omega, all invertible operators. Now we take an A belonging to L, Rn. When is B invertible? See, if this condition is satisfied, then you know that from our considerations that B inverse exists or B is not equal to 0. That's the meaning. B is not equal to 0. So here we push this observation across to higher dimensional spaces where you know that there are a lot of handicaps. In fact, we see that 0 is not the only linear transformation which is non-invertible, but there are plenty of operators which are not invertible. Okay. Therefore, we make a statement of the theorem. So we speculate. What do we speculate? We say that B belonging to L is invertible if B minus A because A is invertible, therefore norm of A inverse is finite. This holds good when therefore we write down the following. We make the conjecture. This is the conjecture. If A belongs to omega, and if norm of B minus A then how the theorem has evolved, you have seen that we can prove it. I think our speculation is right or our conjecture is right. This is how one should investigate on the various results that we come across, because you can see how people would have created such or inferred such things are true because they analyze examples. That's why I said analysis of examples is crucial in the creation of mathematics. All science. All ideas in science evolve out of observations and experimental data. Okay. So here we have the examples. So we went even the very trivial situation of n equal to 1 gives a insight into what kind of results we can expect. Okay. So what does this mean? This means the distance from B to A is less than 1 upon if distance between B and A is less than 1 upon, which means you are talking about a neighborhood of A with radius 1 by norm of A inverse, then every operator in that disk is invertible. Okay, that is every you have is the following. If I designate by n 1 upon norm of A inverse, that is the radius of A is contained in and that's what we have observed in the one dimensional case. Okay, but it's complicated here because you know that there are plenty of non-invertible operators in LR. Let us see how we prove this. Okay, proof is fairly simple. Now put therefore, then what you get? You get beta into. So we have to prove that. Okay, this is the condition. The condition says that beta into norm of A inverse is 1 upon alpha. So you have got 1 upon alpha is less than 1, that is beta is less than alpha. That is the given condition. So these are the given data. Now we will compute it. We will do a little bit of computations. We have seen how the result has evolved from the consideration of one-dimensional space. And I think every case you have to keep analyzing in this fashion. How credible examples you analyze, you will get a lot of insight into what is happening, and good insights turn out to be good theorems. Okay, so what you have for every x belonging to Rn, you have alpha 2 is equal to alpha into, see, you are using A is invertible, okay, this is of course less than or equal to alpha into norm of A inverse sorry, alpha into or let me write here, this is not less than or equal to norm of A inverse into norm of Q. Now what is norm of A inverse? Alpha into this. Now norm of A inverse is by definition 1 by alpha. Therefore this is equal to norm of AX 2. Now this I can write as norm of A minus B plus B to, this is less than or equal to is less than or equal to which implies, where did we start? We started here. Which implies alpha minus beta since alpha minus beta is positive, it follows that Bx not equal to 0 if not equal to, if x is not equal to 0. What does this mean? This means b is 1 to 1 and hence on to, because it's a finite dimensional vector space. So what does this mean? Which implies, what's the theorem with that? Okay. So this is true for all b belong to such that norm of b minus a is less than okay, which implies so the collection of all invertible operators form an open subset of LR. That is the consequence of this theorem. Now the next result that we want to look at is this. Suppose you have, see, omega is open. Is the open subset of all invertible operators on R. Now you see, so A belongs to omega implies A inverse belongs to, obviously 0 does not belong to that. 0 does not belong to it. That is obvious. Therefore, now you can define a map. So define omega by phi of A inverse. Then what you want to assert is that is continuous. It is defined for every A belonging to polygon. So this is a theorem. So let's make this as a statement. Theorem. The mapping phi from omega to omega defined by continuous. It's quite simple. Okay. So we have already that the following property. Let me just write down that. Let me copy. Alpha minus beta norm x from the previous theorem is less than or equal to this is the inequality that we proved to conclude that B is invertible. Okay, now put x equal to B inverse. Because B is invertible, we are assuming the conditions of theorem. So assuming the conditions of the previous theorem. And the notations, the definitions of alpha and beta. Then what do you get? Then this is what you get. Alpha minus beta norm of B inverse y is less than or equal to this was good. So it is just bringing this alpha minus beta inside and norm of Then use this inequality and you get the result. Okay. Therefore, which implies norm of B inverse is less than or equal to that is. Therefore, now let us keep this aside and now we work on this. So we want to work out on this B inverse minus A inverse. Just compute this. Now B inverse minus A inverse is equal to B inverse A minus B A inverse. That's quite easy to compute. Okay, this is easily verified, and this implies norm of B inverse A inverse is less than or equal to norm of B inverse norm of A minus B norm of A inverse. That is there, and this you can write from our definitions of alpha, beta, and alpha minus beta, etc. So you have, so this we have already proved that this is less than or equal to this. So from this, it follows that this is beta divided by alpha into alpha minus beta. Okay, what is this? This is essentially in terms of our map. This is is less than or equal to beta divided by now you see as beta goes to 0, what is beta? You go back to the definition of beta. Beta is norm of so as beta goes to 0, phi b goes to that means the map that associates a vector, an operator with its inverse is a continuous map. That is, phi is continuous. Now what I want to do is just say something about the norm of A. Okay. Basis of Okay. Then you have for an AX, this is equal to sigma summation over I summation over J Aij Cj. Okay. Okay. And this is less than or equal to summation over I summation over J Aij dot Cj square. Okay, this is how I rewrite this. I have used the Cauchy-Schwarz. Okay. Now this is less than or equal to summation over I comma j Aij square into norm of okay. So this is a scalar. Okay. Therefore which means if you have a matrix Aij, suppose this is a matrix of m rows and n columns, then this defines a map from Rn to R. Okay. Then the norm of A is bounded by Aij square to the power R. So this is the estimate of the norm of A. That's it. Okay, so this is a very simple example. So this gives for any now we also use or make a look at the consequence of this result. Okay, consequence of the bound. Okay. So let S be a real continuous functions of that is you have Aij P. Aij is a map from S to R. That's an assumption. For every I and j. Let AP this is the M by N matrix. This is the M by N matrix. Okay. Then for every P belonging to S, AP belongs to L. AP is a linear transformation from Rn to Rn. So you have now for corresponding to each P there is an AP. So you have got S here, SO is there. You have a P here, P is mapped to A. For A, you can think of this as a map. This follows from the above result, because what you have is this, that you see, if you take A of P1 minus P2, AP2, you know that AP1 belongs to that, AP2 belongs to that, then AP1 minus AP2 also belongs to L, Rn, Rm. This is less than or equal to now what's our assumption? This is a finite sum. It's a finite sum. And you see that Aij P1, when Aij P1 goes closer to Aij P2 for all I and j, you see that AP1 goes to AP2. That's what you mean by continuity. So this inequality, this is the previous inequality. Star, you have this. Okay. So because you have AP1 minus That's the matrix. Therefore, this is a continuous. Okay, so from any matrix space, S rho, if you work this out, then this is the of course rho of AB is defined as so that completes the theorem. Okay, so thank you very much.